Hi, folks. Today we're going to talk about patterns. So, to begin with, we're going to start by thinking about a circle and see if we can get some intuition on what it means to be a pattern. And so, consider a circle, take n points on the circumference, and join every pair of points by a line segment. And so, we can see here we have 1 point. There's nothing to make a line segment with. Here we can see 2 points, and we make a line segment across, and we've divided it into 2 regions. When we have 3 points on the circle, well, we have 4 regions. When we have 4 points, we end up with 8 total regions, and so on. And so the question becomes, how many possible regions can the circle be broken into? And so looking at the first few, we have the first one, we have just 1 region, then 2, then 4, then 8, then 16. What do we suspect the pattern is going to tell us when we have 6 points on the circle? Write it down, see if you get it right. But before we come to the answer, let's explore the type of thinking we're doing when we're trying to come to this solution. And so to begin with, we have the idea of a conjecture. And so a conjecture is a type of hypothesis, a premise which may or may not be true. Whenever we're trying to talk about mathematics, we're seeking the truth in one form or another. An example of a conjecture is all prime numbers are odd. Note, turns out they are not. 2 is a prime number and 2 is not odd. And so that is a counterexample to this conjecture. Typically, to come up with a conjecture, we will use some form of inductive reasoning. Inductive reasoning means we're looking for patterns. And so we will look for patterns or supporting evidence and use that to develop a working conjecture. Should we be able to take a conjecture and mathematically prove it using logic, then we may be able to create a theorem, a statement which is provably true. As an example, all primes greater than 2 are odd. In this case, we're dealing with numbers which are strictly greater than 2, and we can look at the definitions of what it means to be a prime number. What does it mean to be odd? And it turns out that any number which is odd is not going to be divisible by 2. So all prime numbers greater than 2, well, they're never going to be divisible by 2, so that means they must be odd. A proof is the application of deductive reasoning to verify that a statement is true. And so deductive reasoning is kind of the opposite of inductive. Inductive is looking for patterns. Deductive reasoning is a way to verify that something is actually true or not. And here we have a breakdown of them. And so in order to get good at mathematics, we need to be able to get good at both inductive and deductive reasoning. We use inductive reasoning to come up with a reasonable conjecture. We then attempt to prove or disprove the conjecture using deductive reasoning. Ultimately, we question everything. If you see a pattern, that's the starting point. That is not the ending point. The simplest forms of inductive reasoning involve pattern recognition. And as humans, we are amazing at pattern recognition. Let's check out some patterns. And so what is a pattern? That might be a first big question. Hopefully, we all know what a pattern is and can recognize one when it happens. A mathematical pattern is some collection of numbers, objects, for which we can infer some connection and potentially predict additional values. Typically, there's an order to this collection where we can try to determine the next values, but there's a lot of different types of patterns. Sometimes it's just going to be a list of numbers. That's the most common one that we're going to see in mathematics. But it could be a list of shapes or some other string of things. Sometimes it's a pattern or a tiling of shapes. And so we can talk about geometric objects and how they are arranged. Sometimes it involves patterns repeated within patterns. That happens often with fractal geometry. But usually there's some recognizable rule to determine elements. So now we just have to get good at pattern recognition. Types of patterns. How many different types of patterns do you know? There's a lot of different types. Let's talk about some of the basics, and above is the Penrose tiling. What is so special about it? Penrose tiling actually came out in 2024, I think it was. It is a pattern, a shape, which can be repeated infinitely. And it turns out as you repeat it out, as you tile a space with these, there will never be a repeating pattern. And that's kind of unique. It wasn't clear that there was going to be such an object. And eventually, this one was discovered. On our journey for patterns, we're going to start with simple repeating sequences. And so a repeating sequence is a sequence which repeats after a certain number of steps. We can see them in numbers. We can see them in shapes. Here I have them with the different colors. If you are dealing with music, every time you are hitting A minor, F, C, and G, and then repeating, that's a repeating sequence. And you can just keep that going for as long as you want. In arithmetic, we often see these in the forms of repeating decimals. And so if you see a repeating decimal, like how about 0.027, 027, 027, on and on forever and ever. That's the decimal equivalent of 1/37th, I believe. And so we can recognize that pattern and say, all right, we understand the pattern. It's going to repeat this forever. A couple more types. An arithmetic sequence is a sequence of numbers which changes by adding or subtracting a fixed amount at every step. And so start at 53 and count backwards by 7. Well, that goes 53 to 46 to 39 to 32 to 25. And you can figure out what the next 3 values in this sequence are going to be. We would just need to subtract 7 again, and then subtract 7 from that, and so on. Here's another example. 13 to 19 to 25 to 31. In this case, we started with 13 and we are adding 6 every time. A geometric sequence is a little different. And so instead of adding or subtracting, we're going to be multiplying or dividing by a fixed amount at every step. As an example, start at 36 and multiply by 1/2 at every step. So you would go 36, 18, 9, 9/2, 9/4, 9/8. You could just keep going on and on and on in that direction. Here's another example. 3 to -6, -6 to 12, 12 to -24. What's happening is we're multiplying by -2 at every single step. The next pattern is a little different. And so this is called the triangular numbers. So the triangular numbers are the set of numbers you get from adding consecutive numbers. And so 1, then 1 plus 2 is 3. Then 1 plus 2 plus 3 is 6. And 1 plus 2 plus 3 plus 4 is 10. 1 plus 2 plus 3 plus 4 plus 5 plus 6. And we can continue this pattern forever. So here we can see the listing is 1, 3, 6, 10, 15, 21, and so on. We can also use functions in order to describe patterns. And so some functions are easy enough to understand. Functions are an Algebra 2 idea of basically a formula for producing values. And so if we think f of n is equal to n squared, well, when n is 1, we get 1. When n is 2, we get 4. When n is 3, we get 9, then 16, and so on. Same with n cubed. Well, now it's just cubing every number. So 1, 8, 27, 64, and so on. The next one is 2 to the n minus 1. And so 2 to the 1 minus 1 is going to be 0, then 1, then 3, then 7, 15, and so on. The next one, f of n is equal to n minus 1 over n plus 1. We get a string of fractions out of this one. It might be a little bit harder to recognize the pattern when just looking at the fractions, but you can still figure it out. Here's one which is -1 to the n plus n. Again, it's going to be a little bit harder to figure out until you have more values. And then this one, cosine of pi n log base 2 of n. Well, that's a very complicated one. Here's the graph of the function. If we were just going to be choosing the values at every single value, we're going to go 1 is 0, then 1, then negative 1.58496, then 2, and so on and so forth all the way through. These functions, they can get pretty messy, but each one is really just giving us some type of pattern that we need to be able to follow. The next one is the Fibonacci sequence. Fibonacci sequence is a very powerful one and an example of a recursive sequence. With Fibonacci sequence, you start with values 1 and 1, and then every value after that comes from adding the two previous values. And so 1 plus 1 is 2. Well, then we do 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 and 13 is 21. 13 and 21, it's going to give you 34. And you can just keep going from there as you go. Other variations, such as Lucas numbers, follow this pattern, but start with different numbers. And so what if instead of starting with 1 and 1, what if you started with 1 and 3? How would this sequence be different? The Fibonacci sequence and Lucas numbers are examples of recursive sequences, a sequence for which new values are based on previous values. Sometimes it's going to be based on just the previous one value. Sometimes it'll be based on multiple values. You could have it be defined on the 5 previous values if you really wanted to. For this example, let x sub 1 equal 2, let x sub 2 equal 5, and then let x sub n, so whatever the next value is going to be 2 times the 2 values before it, minus 1 times the value 1 number before it. And so looking here, we start with 2 and 5, and then we're going to do 2 times 2 minus 5, which is negative 1. Then it's 2 times 5 minus negative 1, which gives us 11. Then it's 2 times negative 1 minus 11, which ends up giving a negative 13. And we can continue this all the way out. These types of sequences are very common in nature for a number of reasons. The big thing is this is an example of an iterative process, something which is repeating over and over again, basing itself on whatever the previous state was. And that's how nature operates for the most part. Hey, that brings us to the idea of iterated functions. And so some recursive patterns come from repeatedly applying a function such as a piecewise function. And so here is a function. F of n is equal to n over 2 if n is even, and 3n plus 1 if n is odd. And so if you plug in 7, 7 is odd, so you would multiply it by 3 and add 1. So 7 times 3 is 21, plus 1 is 22. If we take the 22 and plug it in, well, 22 is even. And because 22 is even, you would divide by 2. From there, we can see we get 11. 11 is odd, so we're multiplying by 3 and adding 1, which gives 34. 34 is even, so we're dividing it by 2, which gives 17. 17 is odd, so we're going to be multiplying by 3 and adding 1 to give 52. Which is even, so we get 26, which is even, so we get 13. This pattern is going to go on for a while. And so the question becomes, what is the long-term behavior of this? For this one, this is part of a problem called the Collatz conjecture. The idea behind the Collatz conjecture is if we repeat this process forever and ever, will we eventually get 1? Now, there's a lot of evidence saying that, yeah, this is probably going to go to 1, but we can't be sure unless we can actually prove it. And no one has been able to prove it for over 150 years. And so it is still an open proof. To iterate a function means to just repeatedly apply the function over and over. And that's what we did in this case. And that's kind of what we do with recursive functions as well. The next one is Pascal's triangle. Pascal's triangle has a lot of patterns in it. And so Pascal's triangle is a triangle which begins with 1 at the top. And then every value beneath it is going to be the sum of the 2 values directly above it. If there's nothing directly above it, then it's just the previous value. And so here we see 1, then 1, 1, then 1, 2, 1, because 1 plus 1 is 2. Well, then we have 1, 1 plus 2 is 3, 3, and 1. Then we get 1, 4, 6, 4, 1. Then 1, 5, 10, 10, 5, 1. There are a lot of different patterns that arise from this. And we can keep going as long as we like with this thing. But when we start to look at some of the diagonals, well, we see the first one is all ones. The next one is 1, 2, 3, 4, 5, 6, 7. The next one is 1, 3, 6, 10. That might not look recognizable, but it should. Those are our triangular numbers. We can also shade regions which are odd and which are even and get interesting results out of that. We can also actually prove that this thing gives us the powers of 11. And so 11 to the 0 power is 1, 11 squared, or sorry, 11 to the first is 11, 11 squared is 121, 11 cubed is 1,331, and every single row is going to give us some other power of 11s. We also use this for binomial distribution. I mean, there are a lot of patterns that come out of Pascal's triangle, and so it's a good one to know about. We then have patterns from recognizable numbers. So sometimes a pattern will utilize a recognizable irrational number. And so an irrational number is a number which goes on forever and ever and never repeats. And so pi or e are common examples. Well, pi starts with 3 and is 1, 4, 1, 5, 9, 2, 6, something like that. E is a similar one. It's 2.718281828459045, and it just keeps going on and on in some non-repeating pattern. We can use these values to create some type of recognizable pattern. The challenge is there's only so many recognizable irrational numbers. I mean, the golden ratio is one which pops up a lot. It's the ratio of the values in the Fibonacci sequence. Well, I don't know how many folks recognize the golden ratio as 1 plus the square root of 5 over 2, but it's just going to give us 1.618 and something messy after that. Having recognizable irrational numbers can be tricky. We don't have to have numbers, though. And so another example is symbols and shapes. While most of our examples involve numbers, any symbol or shape can be used for patterns. These can be very easy and straightforward or very, very difficult. You'll often see these pop up on things like IQ tests where you're trying to figure out what patterns people are able to recognize. In this case, I feel confident that we are going to have the 3 triangles. And so I'm guessing it's this one. We also have symmetries. And so symmetries are a way of understanding patterns as well. And so in functions and geometric objects, sometimes you're going to see patterns like this. There are different symmetries, like you can have reflections across one of the axes. In this case, this would be a reflection across the y-axis and a reflection across the x-axis. We also sometimes have rotational symmetries. Rotational symmetries means we could rotate everything here, maybe 45 degrees or maybe 90 degrees, and get the same thing over here. In this case, it doesn't look like we're going to have that type of rotational symmetry. But we do have some rotational symmetry. If we take this and we rotate it 180 degrees around our center point, we would end up getting values down here. And so, for instance, this value here, if we rotate it 180 degrees, we're going to get this value down here. Now, the question becomes, can we expand on this pattern? What would happen if we were to go another 5 blocks out in every direction? Could we figure out what the pattern is at that point based on what we already have? That's a harder challenge. The next one we have is geometric tiling. So geometric tiling is a process of applying shapes, often repeated, to see what forms of local symmetries may arise. This is common for rainy day activities in the classroom. The idea of you get all of these little wooden blocks out and see what types of patterns people are able to make in the classroom. It's a nice little education tool to help folks learn about the different shapes and different angles and what types of shapes can be put together. For instance, with this one, you'll often see your trapezoid, your square, your diamond, or your rhombus, and then you'll see a hexagon, but you won't often see a pentagon, which only has 5 sides. The reason for that is the angles just don't match up quite as nicely. Fractal geometry is another example where we are going to see patterns. And so fractal geometry is where we are seeing some shape which is being manipulated in some repeating pattern. It has some form of self-replication and self-reflection. Looking at this one, we start with a triangle and then we're breaking every single line up so that there's an additional triangle in it. And then we repeat that. Every line we replace with something which has a little triangle sticking out. And we can continue this infinitely. Fractal geometry is something which is mostly from the last century or so, once we had computers which were able to handle it a little bit better. But it's a very recognizable type of pattern. Music. Who doesn't love music? And so patterns do not need to be written or related to shapes. Patterns can engage with other senses. Music is one of the key ways in which we engage with patterns related to sound. So often we don't think about it until a note is played and you think to yourself, that didn't sound right, which, that's a big part of certain genres of music. There's a reason why the most popular calculus book has an instrument on the cover. The idea is when we're thinking about music and rhythm, things like that, it's all about having some form of repeated pattern. And we as people are able to recognize that repeated pattern very well. And so now let's go back to that introductory question I asked. Consider a circle, take n points on the circumference and join every pair of point by a line segment. How many possible regions can the circle be broken into? For the first few, we have 1, 2, 4, 8, and 16. What happens when we have 6 points on the circle and connect all of the line segments? Well, we might expect 32, because this is just doubling every time. The reality is, it's only 31. 31 is the absolute maximum, and it's something which you can prove. There's only a possible 31 spots that we can get out of this. And this is one of those places where inductive reasoning leads you in the wrong direction. And this happens a lot, where we see some pattern and we recognize the pattern and we try and use that to figure out what different behavior is going to be in the long term. Well, inductive reasoning usually will get you to the answer, but not always. And this is an example where inductive reasoning fails. We need deductive reasoning. And that's really what separates math and the sciences. When we think of science, it's all about observations and testing. When we think about mathematics, it's less about observations and it's more about trying to deduce what the truth is for abstract shapes. And so here is a circle, and when we have 6 points on the boundary, we're only going to get 31 different regions instead of the 32, which we might have suspected. Final thoughts on patterns. What's been introduced here is simply a selection of patterns, most of which you have probably seen before. The goal is to get you thinking about patterns and about inductive and deductive reasoning. We want you to start asking mathematical questions based on mathematical observations. And once you've asked the mathematical questions, we want you to have the tools to find your answers. That's going to be a big part of this set of videos. We're going to begin by introducing a number of different structures, and then we're going to ask you to explore the different structures which we introduce. With that, I'll let you get to work exploring where you find patterns in the real world.